Let's talk about Class A amplifiers and their efficiency. First of all, what's a Class A amplifier and why do I care about its efficiency? Let's take a look at a common collector amplifier that's used resistive biasing. We have an AC signal entering the amplifier. We might have a little bit of attenuation at this point. That signal reaches the base of our transistor, and the signal then reaches the emitter of the transistor and makes it across the capacitor to our load. That's if everything is going well. This is what we want. If this is what we have, then this amplifier is called Class A. Class A basically means the transistor is always on. It's not in cutoff, it's not in saturated, it's always on, or it's in the forward active mode, in other words. That means that when the signal reaches its highest point, the transistor is in the forward active mode. This also means that when the signal reaches its lowest swing at the input side, the transistor is also in the forward active mode. If the transistor were to somehow switch into the cutoff mode or into the saturation mode at any point of this signal swinging from high to low, then it would not be called Class A. Consequently, we would see clipping in the output. If we don't see any clipping, then it's a good indication that the transistor stayed in the forward active mode the whole time, and then we would call it a Class A amplifier. If you hear other letters like Class B or Class C or Class D, it means that the transistor is not in the forward active mode all the time. You might think, well, why would you want something like that? Well, as we'll see in a moment, Class A amplifiers, while they're nice and good and everything, they're not very efficient. That will motivate us to look at other classes of amplifiers soon. What I want to do now to simplify our analysis is to look at a slightly idealized amplifier. I'm going to assume that we have a source that doesn't have any source impedance, and we're going to assume that the load resistor is rolled into the emitter resistor. So in this example right here, let's consider RE as our output resistor. I'm also going to be assuming that R1 and R2 are large resistors. That way I don't have to worry about using up some power in the bias network on the left. I'm going to assume that beta is large, so we don't have to worry about the base currents. I'm going to assume that the VCE saturation is small. That way I don't have to worry too much about transistor to transistor variation. And then finally, as I mentioned, I'm going to assume that RE is the load resistor. My goal is to find the efficiency of this amplifier. So we're going to have to define efficiency. What I'm interested in knowing here is power out divided by power in. But specifically, I'm going to be thinking about the AC power that makes it to the load. I know that I said the emitter resistor here is our load, and you might be thinking, well, that resistor is going to have some DC current and DC power, and it's also going to have some AC current, AC power. I'm just going to be thinking about the AC power. We're going to neglect the DC part. So our efficiency is going to be the AC power going out, and we're going to divide it by the power coming from our power supply. Because beta is large, we can assume that all of the power driving the load resistor ought to be coming from V sub P and not from our signal. So I'm going to basically neglect anything that comes from our small signal. Let's assume that we have a purely AC signal and this capacitor is large. The signal without any source resistance will then just appear at our base with an appropriate DC offset. If everything is going well, that signal will then appear at our emitter as well. The questions that I want to ask now are how low it can go before the transistor has a problem and how high it can go before the transistor has a problem.
The reason for that is because I'm interested here in knowing what the maximum efficiency is. Our equation for efficiency tells us that more AC power out will give us a higher efficiency, so it's easy to see that the amplifier is most efficient when the amplitude here at the emitter is as high as possible without the transistor exiting the forward active mode.
On the low side, it can't go below zero. Why can't it go below zero? Well, if it were to go below zero, it would mean that current would have to flow upwards from ground through resistor R sub E. That's impossible because current can only flow downwards through that forward bias junction at the emitter. So there would be a contradiction there. Zero is the limit. Now, how about on the upper side? When would the transistor saturate? Well, it can't go higher than Vp minus my saturation voltage. I've said over here that I'm going to assume that the saturation voltage is small, so let's neglect it. Effectively, it can't exceed the power supply voltage. Those are the conditions that have to be satisfied for us to avoid clipping in the output. We don't want the signal to be clipped because we're talking here about Class A amplifiers. Let's draw a little graph of the voltage here at our emitter. So I'll call it VE, and we'll make a graph with respect to time. We know it can't go below zero, so if we assume that it's sinusoidal, then if we plot one period, then it should just touch zero when the sine wave is at its minimum. We've also said that it can't exceed V sub p, so I can say that it should just touch V sub p when it's at its maximum. So we have 0, Vp, and then because of symmetry of a sine wave, we can just identify this as Vp over 2. I'm interested now in writing an expression for our emitter voltage. We have a DC offset of Vp over 2, and then we have a sine wave with an amplitude of Vp over 2. We'll say it has an angular frequency omega. Of course, we could have some other time-varying voltage as well, but we're going to focus first on sinusoids. What's our expression for the total emitter current? Well, as a function of time, it's just going to be VE divided by RE due to Ohm's law. So this is fairly easy to work out. We just need to divide everything by R. This is the AC portion of the emitter voltage, and this is the AC portion of the emitter current. I'm interested in calculating the efficiency, so I'm going to need the AC power out. Using the AC portion of this expression and the amplitude, Vp over 2, I can write what the AC RMS voltage is here at the emitter. I just need to divide that amplitude by the square root of 2. I can do something similar here with the emitter current. I can take the AC portion of it and identify an RMS AC emitter current by looking at the amplitude and dividing it by the square root of 2. Let's calculate now the output AC power. It's just going to be VRMS times IRMS, and I have two expressions for voltage and current. If I multiply these times one another, I wind up with V squared in the numerator, and then I wind up with 8RE in the denominator. So I finished the numerator portion of my efficiency expression. Now let's find what the power in from our power supply is. Well, power is just voltage times current. I have an expression for the current. It's just IE as a function of time, and the voltage is just constant. It's Vp. So the input power is going to be given by Vp times IE, and I want the average power, so I'm going to have to take the average over one period. So let's use an integral. So t here represents the period. That's this amount of time. And I'm going to integrate over a full period. This will give me the time averaged power. And now inside the integral, I need voltage times current. So the voltage is just Vp, it's constant. And for the current, I'm going to have to substitute in IE. We can pull Vp out of the integral because it's just a constant, and we're left with my emitter current. It has two different expressions. We have a DC offset and an AC component. Let's look at the second integral first. We're integrating a sine wave. if we integrate a sine wave, we're going to wind up with a cosine. And if we evaluate a cosine over one period, it's going to be 0. Think of it this way. If you're integrating a sine wave, the sine wave spends half of its time above 0 and half of its time below 0, so the two areas cancel each other out. The second integral will be 0. We only have to worry about the first part of the integral, and it's just a constant. I can pull everything out of the integral, and I'm left with the integral of dt. So if you integrate dt over one period, it's just t. The t's cancel, and we have a final expression for the input power. Let's now find our efficiency. AC power out is this expression with an 8 in the denominator, and total power in is this expression with a 2 in the denominator, 25%. It turns out that 25% is the highest possible efficiency for a Class A amplifier if you're using resistive biasing and you're talking about sine waves. If we were to somehow allow more AC power at the output without using a sine wave, then we could improve the efficiency a little bit. One way you could do that would be, for example, to use a square wave. By assuming everything as a sine wave, though, you're making a very reasonable assumption about the efficiency.
Hopefully now you can see, by the way, why I made all these assumptions when I started the calculation. If I had assumed that R1 and R2 had been small rather than large, or if I had assumed that the beta is small, or if I had assumed that the VCE saturation was not small, or if I had included a separate load resistor, then the efficiency would have been lower than 25%. What I've done here is calculate the maximum possible efficiency for a common collector amplifier with resistive biasing in the Class A mode.
This will allow us to compare different types of amplifiers. Let's now look at common emitter amplifiers. We're going to start with the same assumptions. I'm going to assume a very small source resistor. I'm going to assume that R1 and R2 are large, that the saturation voltage of the transistor is negligible. And in this case, to start off, we're going to assume that our load resistor is rolled into our collector resistor. In a common emitter amplifier, we have an AC signal that makes it to the base of our transistor and then shows up at the emitter. In order to simplify things here a little bit, we're going to maximize our gain and assume that this emitter resistor equals 0. We're still going to have to be careful not to cause the transistor to go into saturation or cutoff, but this will maximize the gain in any case. That AC signal will show up at our collector. And now the questions I want to talk about are how low it can go and how high it can go before our transistor starts to have a problem.
Just like before, I'm going to be interested in knowing what the maximum possible efficiency is, and the maximum efficiency will occur when the output voltage has the highest amplitude.
If our emitter is grounded, then it's not going to be able to drop below VCE sat because I need at least that VCE sat on the transistor to keep the transistor from saturating. If I assume that VCE sat is small, I can effectively say it can't fall below 0 volts. How high can it go? Well, it's not going to be able to rise above the power supply voltage. Otherwise, current would have to go the wrong direction through the transistor. Let's now make a graph of the collector voltage as a function of time. So we'll call it V sub C. And we'll assume that it's sinusoidal. We'll draw one period of it. And at its lowest point, it just touches the saturation voltage, or in this case, we're just assuming that it's close to 0. At its highest point, it just touches the power supply voltage. That's V sub P. By inspection, we can see that the average voltage is just Vp over 2, and we can go ahead and write an expression for the collector voltage as a function of time. So we have a DC offset, and we have a sine wave with particular amplitude. I'm interested in calculating the efficiency. This kind of an amplifier where you have some DC component and AC component flowing into the load resistor is called a single-ended amplifier. I'm interested in knowing how much of the AC power gets delivered to the load. I don't care about the DC offset in the load. Let's then just write an expression for the AC portion of the collector voltage. So it's just the second half of this expression. I see the amplitude right here, so I can identify what the RMS collector voltage is. I just need to divide that amplitude by the square root of 2. The power delivered to the load, which in this case is RC, is the RMS voltage squared divided by the load resistor. So if we square this expression here, we wind up with 8 in the denominator, along with our RC. Now what I'd like to do is find out how much power is supplied by our power supply. So for that, we already know the voltage is just Vp. I need to know what the current is. Let's label that current as I of t. In order to find this current, I'm just going to apply Ohm's law across resistor RC. I equals V over R, so we have Vp on one side and Vc on the other, and RC in the denominator. So let's just write out this expression, and I need to now subtract my collector voltage. So we'll write the entire expression for the collector voltage from up here. So simplifying a little bit, we can get a final expression for the current coming out of the power supply. To find the power delivered by the DC voltage source, we need to find the time averaged power. So let's integrate over one period where this is one period, and we'll use the expressions for the voltage and current. So the voltage coming out of this power supply is constant. It's just V sub P. And the current is I times T, and we have an expression for it down here that we've just found. When we integrate a sine wave over one period, we're going to wind up with 0. So the integral simplifies considerably. We're just left with V squared over 2R. Let's now find the efficiency. So the efficiency is the power delivered to the load, or the AC power delivered to the load, divided by the power supplied to the amplifier. So here's the power delivered to the load, and if we divide that by the power supplied to the amplifier, we wind up with 0.25, or 25%. So we again conclude that a Class A amplifier is having a maximum efficiency of 25% if we're dealing with sine waves. Let's now look at current source biasing using the common emitter configuration. We'll again start with the same set of assumptions as before. We have an AC signal entering our amplifier and finding its way to the base of a transistor. The signal then shows up at the emitter, and to maximize my gain, I'm going to assume that the emitter resistance is 0. The transistor will have some particular VCE saturation voltage, but we're going to assume that it's small. The AC signal at the emitter is inverted, and it winds up at the collector. The AC portion of it is extracted and delivered to the load through that capacitor. The question that I'm interested in answering right now is how high that voltage can go and how low that voltage can go before our transistor starts to have a problem.
The reason why I'm interested in the maximum possible swing here at the output is because that's going to correspond to the maximum possible efficiency for the Class A amplifier that we have drawn here.
On the low side, we know that it can't drop below the saturation voltage of the transistor. If we assume that that's a number close to 0, I can effectively say that it can't drop below ground. Now, how high can it go? Well, at its highest point, that means that all of the current from this DC current source should be driving our load, and no current would flow through the collector. If any of it were to branch off and flow through the collector, then it would lower down the collector voltage a little bit. This gives us enough information now to make a small plot of the collector voltage as a function of time. At the minimum, it's not going to drop below 0, and at its maximum, we have V equals IR. Let's write an expression for the collector voltage as a function of time by referring to our graph. So we have a DC offset of our voltage. It's just IR over 2. And we have superimposed or added to that a sine wave with an amplitude of IRL over 2. Our load voltage only sees the AC portion of our collector voltage. So the capacitor effectively drops this first term here, and we'll note just the AC portion. I can see the amplitude, and because it's a sine wave, I can identify an RMS voltage. This gives us enough information to find the power delivered to the load. It's just the RMS load voltage squared divided by the load resistor. So we wind up with I squared R squared divided by R over 8. Now to find the efficiency, we should find the power supplied by our DC current source. You'll notice that there's no VP showing up in my expressions at all. These sources are somehow mathematically the same, or they're mathematically combined here. The DC current source supplies whatever current is necessary to maintain voltage V sub C. So we can integrate over one period V times I. So current is constant, and then we just need to substitute in our expression for the voltage as a function of time. Since the current is a constant, we can just pull it out of the integral and integrate the voltage over one period. We have an expression for the voltage up here already, so we can just note it again. When we integrate over the sine wave, we're not going to get anything interesting. And the rest of our integral just has a bunch of constants. Let's now find the efficiency of our amplifier. So our efficiency is just power delivered to the load divided by power supplied to the amplifier. Notice that we again have a ratio of 0.25 or 25%. So you might think at this point, well, it's somehow obvious that all the Class A amplifiers can have efficiencies of 25%. But let me show you an example with inductive biasing where that's not the case. We can do a little bit better. Let's again start with the same set of assumptions that we've been looking at. We're again going to be assuming that the source resistance is 0. We're assuming that R1 and R2 are large, so we don't have to worry about power consumed by the biasing network on the left. We're going to be assuming a very good transistor with a really large beta and a really small saturation voltage. And then to maximize the gain here, we're also going to be assuming that the emitter resistance is 0. Our signal enters the amplifier, and if we neglect the source impedance, it all winds up over here on the right at the base of our transistor. The signal shows up at our emitter, and at this point, it then becomes inverted, winding up at our collector. Because of the inductor, though, we know that the average voltage has to be VP. So that means that the midpoint of our signal is actually going to be VP. The signal can swing up higher than our power supply voltage because of the inductor. The question here is, how high can it swing and how low can it swing? It's easier to answer it on the low side first. How low can that signal swing? Well, it can't get below VCE sat, can it? Because that would drive the transistor into saturation. So it can't go below VCE sat, and we're kind of assuming that's a small number. So it can't go below ground. How high can it go? Well, because we already know what the midpoint of the signal is, we know from the symmetry of the sinusoid that it can't go above 2 VP. Let's call this voltage our collector voltage and make a plot of it as a function of time. The midpoint of the signal is our power supply voltage Vp, and the AC signal sometimes swings down and it sometimes swings up. At its lowest point, it just touches ground, and at its highest point, it touches 2 Vp. From this graph, we can come up with an expression for our collector voltage as a function of time. Our collector voltage has a DC average and a sine wave added to it. Our load voltage is just the AC portion of our collector voltage. The capacitor filters out the DC offset. The RMS load voltage can be extracted from the amplitude of our load voltage by dividing it by the square root of 2. Since we're trying to find the efficiency, we're going to have to find the power delivered to the load resistor. So we'll take the RMS voltage squared and divide it by RL. In this case, we wind up with Vp squared over 2RL. Let's now assume that we have a DC current I flowing through this inductor. If it's a very large inductor, then I expect it will block the AC portion of the current. We can almost treat it like a current source in such a situation. Let's call the current here flowing into the transistor our emitter current. I'll label it IE as a function of T. It's just equal to our collector current. That emitter current has 2 components. It has a DC component that comes down through the inductor, and it has an AC component that's coming from the load. Using Ohm's law, I can identify that AC current coming from the load is V over R. It's quite easy because I know that all of the DC current has to come from the power supply and all of the AC current has to come from the load. It can't be the other way because the DC current is blocked by a capacitor and the AC current is blocked by an inductor. Let's now find the total power supplied by the amplifier. We'll call it PV. So let's integrate again over one period. And we need the voltage times the current. Well, the voltage up here is just constant. And the total current supplied is given by I, coming up with a final expression of VI. The efficiency of this amplifier is given by the power delivered to the load resistor divided by the power supplied to the amplifier. Let's simplify that just a little bit. In order to find out what current I we need to use, let's return for a moment to our expression for the emitter current as a function of time. We know that this has to be larger than 0 all the time. Our IE min, or our minimum value, is going to be this DC current minus 1 over RL, and now we can look at our expression for the load voltage and notice that it has an amplitude of Vp. That means it won't swing any lower than that. The emitter current should reach 0 when our signal swings the lowest. This means that our I should be V over R. If we substitute that into this expression, we wind up with an efficiency that's 1/2. In other words, the efficiency of this Class A amplifier is 50%.
Keep in mind that 50% is the maximum possible efficiency. If the gain is a little bit low or the load resistor changes a little bit, then the efficiency would drop because the output voltage amplitude would also fall.
It's kind of interesting, isn't it, that the use of an inductor in the biasing network allowed us to double the potential efficiency of our Class A amplifier. These were all compared using sine waves, so all of the comparisons are reasonable. Generally, with resistive biasing, you can achieve about 25% efficiency with a Class A amplifier. With inductive biasing, you can achieve 50% efficiency. But neither 25% nor 50% are very satisfying, for example, in power applications. If you want to amplify a large signal and you're burning up half or 75% of your power in the amplifier itself, then that's not very good. That motivates us to look for other potential ways of improving the efficiency. We're going to be looking, therefore, at amplifiers that are Class B, Class C, or Class D. In other words, where the transistor is not always in the forward active mode. That's going to be what allows us to improve the efficiency of these amplifiers. That's what you can look forward to in subsequent videos.